So what we're looking at today is an extension of our favorite theorems from derivatives, which are the mean value theorem and Rule's theorem. So we're going to take like the antiderivative variation of those two theorems, and we're going to apply them. So yes, we're taking Rule's and MVT, and we're applying them to antiderivatives. And MVT. So there's a mean value theorem for integrals. So MVT is when the slope of the secant equals the slope of the tangent. Correct. And then the Rule's theorem is where it equals 0. But in order for Rule's theorem to exist, f of b has to equal f of a. There are 3 rules for Rule's theorem, and MVT says that the slope of the secant equals the slope of the tangent. The f of, yes, so, okay. The first two repeat themselves. So the first one is that it is a differentiable and closed interval from a to b.
Right.
And then it has to be continuous on a to b.
Right.
And then for Rule's theorem, it says that f of b equals f of a.
Right.
Mean value theorem says that f of b minus f of a all over b minus a equals a number. And then you set the derivatives equal to that number in mean value theorem. And then in Rule's theorem, you set the derivative equal to 0.
Correct.
And then you have IVT, which is like completely different, and that's the one that doesn't involve the integral.
Right.
I mean the derivative, sorry. Okay, average value of a function. Think about what the word average means. So, and think about where we see the average. So we just related and went backwards and kind of talked about mean value theorem. And if you think about the mean value theorem, you kind of were averaging out the slopes.
Yeah.
So in average value of a function, we have that same sort of concept. So it says, suppose you wanted to take the average temperature during a 24-hour period, or just one day. How could you do it? So what we'd have to do is we'd have to get a bunch of different temperatures from throughout the day, add them all up, and then divide by however many we found. So if we recorded the temperature every hour, then we would sum the 24 temperatures together and then divide by 24. So if we said that f of t represents the temperature at time t measured in hours since midnight, one way to start is to measure the temperature at n equally spaced times and then average those temperatures, which would look like f of t. And then let's say that we have n sub 1. And then we're going to take f of t at time 2. We're going to take f of t at time 3. And we're going to take that and we're going to keep adding all of these f of t's together until we get to whatever t sub n number we looked at. And then since n is the last temperature we would take, we would divide by n numbers of temperatures. So again, I said every hour, you divide by 24 hours. If I took 12, then I'd divide by 12 times. If I only did it every 6, I'd divide by 6. So that's where the t sub n kind of comes into play. It says, okay, you took this many temperatures and we divided by that many. It's easy to see then that the larger the number of measurements, the more accurately this will reflect the average temperature. And that's directly relating back to Riemann sums. So as we looked at Riemann's, we said, okay, the more subintervals I take, the better my average or my area under the curve is going to be to the real one. So if I took more Riemann sums and I made more rectangles and I summed those up, then those sums became closer and closer to the actual sum. So the same would be true with the average temperature. The more I take, the more accurate they would get. So this can be written as a Riemann sum by first noting that the interval between measurements will be. So let's say that we make the interval between the measurements equal to n still, where there's 24 hours in a day. And we're dividing them into, we don't quite know, but we're dividing them into equally spaced out t's. So we could do a substitution into the problem, and instead of saying we're dividing by n now, I could say I was multiplying. So again, we are normally dividing, so you have all the stuff up top, dividing by n. So if n is equal to 24 over delta t, I could flip n, so it's 1 over n, and say that delta t is divided by 24. You see the connection? This is equal to delta t over 24. So if n is equal to 24 over delta t, 1 over n is equal to delta t over 24. Go back to the equation we just made above and substitute this in for your n. So now I have delta t all over 24, and I'm still looking at f of t sub 1 plus f of t sub 2 plus all the way to f of t sub n. This right here represents a sum, right? The area under the curve is really a sum. And that's what we talked about, where we express the integral as a summation limit. So what I can do is take this last expression here, where we plug delta t in for 24. When we have delta in anything, that's kind of like the same as saying the width of the rectangle. So this delta t is the width. All of these would represent what? Okay, but what other word did we use for the Riemann sum? Yeah. All of these would represent heights of rectangles. So what's new is the 24. The 24 is bringing in the average. So what I could do is I could think of this as a summation, right? So this is a sum of all the f of t's being compared with delta t from n equals 1 to k. What's new is the 24. So here's your Riemann summation. How do we write a Riemann sum as an integral? Right? So here's my integral. The f of t part stays, but we drop kind of like the sub n thing. What do you do to the delta t? What would that become? dt, where the delta changes to a d. So there's your dt. Okay, all with the 24. It's going to be my denominator, right? And we said that we were taking this over a 24-hour time period. What can I do to that constant that we have in the bottom of the denominator? Bring it out, right? So when you have constants, we bring them out. So I could actually bring it out as 1 over 24, 0 to 24, f of t dt. Why look at all this? Well, when we talked right at the very beginning, I said, what if you recorded the temperature every hour? and you summed up all those temperatures, and I said if you wanted to find the average, you would divide by 24.
Yeah.
So here's your division by 24, taking the temperature every hour. So this integral right here sums the temperatures from midnight to midnight the next day, and then finds the average of them for that 24-hour time period. So instead of having to write down the temperature every hour and sum them all up, you can actually do it. For the very, very last part. Tomorrow. With driving papers that I gave you on Wednesday. It's supposed to be due tomorrow. And be due Wednesday. Wednesday. Because your test is going to be Wednesday. So we're going to review tomorrow. Not test, it's a quiz. But I want to give you a quiz. Okay. So the question comes up then, if that integral represents the average temperature during the course of the day. So think about even the news every day. They say, all right, there's a high of blank, a low of blank, and then they can say, so the average temperature for the day would be, let's say, in comparison even to today. Let's say it's a high of 51, a low of 22. They might say the average temperature over the course of the day is going to be 42 degrees. So on average, if you go outside, it'll feel about 40 degrees. Do you think that there's any point during the day that the temperature reading on the thermometer will be the exact same value of the average temperature? Okay, yes, that is true. So this is where those theorems that we've talked about are coming back into play. If the temperature for the day is calculated to be an average of 42.1 degrees, at some point during the course of the day, the temperature was most certainly 42.1 degrees, because temperature cannot spike from one to the other. You have to go slowly over time or quickly over time, but it never skips a degree. We can say then, in general, do we have any idea what the equation for average value of a function would look like, taking the temperature example into play? So like I asked if you think you could come up with the average value integral, taking into the example we just did, because I gave you the average value of the temperature. So we know for sure it'll have an integral. Yep. Very good. So it's going to go from A to B, and then it's going to be, to get the average, 1 over B minus A, because you want to average all of these sums. So it's kind of like f of, and it doesn't matter, you can make it f of x, f of t, whatever, but whatever variable you put here, you got to put that. And can you see how this, again, remember, the integral represents a sum. So this is the sum of all the terms from B to A divided by the average sum of B minus A. So again, it's easy to think over the average value of a function as the integral over the interval where B minus A is the length of it. So what I'm saying down here is it's kind of like the same as saying, okay, you have the integral of A to B of f of x dx all over B minus A. So the sum of all the items divided by the number of items. So here's your average. So let's actually find the average value of a function. So now we said that f of x is equal to 4 minus x squared on the closed interval 0 to 3. And then we want to know, does f actually take on this value at some point in the given interval? what would the function 4 minus x squared look like? The parabola opened down, right? And shifted up 4. So it's 0, y is 4. At 3, where would we be at? 4 minus 9. How about a 2? And that 1. So we're talking about this region in here. So as an integral, this would be the integral from 0 to 3 of 4 minus x squared dx. And then to find the average of it, we do 1 over 3 minus 0 out in front. So this right here represents the average of f. So to say the average value function, you put an a and a b for the average. So this is the AVF. 1 over 3 minus 0 remains a, 1/3. What's the antiderivative of 4?
4.
And the antiderivative of x squared? Yep, so you add 1 and divide by that new exponent. So you get x cubed all over 3. Here, this is like x to the 0, so it's like x to the 1 all over 1. So you go from 3 to 0. So what we're going to do is we're going to take 1/3, keep it out in front. I'm going to plug 3 in for x's here. So you have 4 times 3 minus 3 cubed, which is 27. Then 27 divided by 3 takes you back to 9. And really, this is 12. So that's the f of 3 minus f of 0. So you take 0 and plug it in. Well, 0, 0. So you get 0. So 12 minus 9 is 3. 3 minus 0 is 3. 3 times 1/3 is 1. So again, this 1 right here represents the average value of the function from 0 to 3. So the next part of the question says, will the function actually take on this value at a given point in the interval? Yes. So what you want to do is you want to take the function and set it equal to 1. So again, you can kind of see that connection to the average value and what we're doing. So take 1, replace f of x, and set it equal to 4 minus x squared. Okay, so if you subtracted 4 from both sides, you got -3 equals -x squared. So you could cancel out your negatives. So 3 equals x squared. Here's the case where you got to remember the plus and the minuses. So really this is plus or minus the square root of 3 equals x. However, I realized that the negative square root of 3 wouldn't be on my closed interval. So the only value in my interval would be x equals √3. So you would say at x equals √3, the value is the same as the average value of F. Okay, let's look at the next example. So the average value of F on the closed interval 0 to 3 is 1.
Yeah.
So at x equals root 3, the value of x equals root 3 is the same as the average value, which is 1. So if you plugged root 3 in,
I get it. I'm just saying, I'm thinking about the way you
as long as you're not ambiguous. So like here, I said AVF equals that, which is 1. So like at x equals root 3, the value is the same as the average value. I mean, you could say which is 1. But okay, go ahead and set up a simple graph for g of x. Okay, so it's just a square root. So what do you know about a square root? Type of shape is 1 minus x squared going to take on a circle. And then the 1 is shifting it up 1 unit.
Right.
So find the value of g of x equals 1 plus the square root of 1 minus x squared on negative 1 to 1. Again, the other option is to say, okay, let's plug in some of these values. So you need to know negative 1, you need to know 1, we'll probably need to know 0. So when x is negative 1, negative 1 squared is 1. 1 minus 1 is 0. Square root of 0 is 0. So we got a positive 1. Plug in 0. Get 1 minus 0. So square root of 1 is 1. 1 plus 1 is 2. And then if you plug in 1, you're going to get the same as when you plugged in the negative 1. Go back to 1. So again, what we're looking at is a semicircle shifted up 1 unit. So when we talk about this, talking about the area under this curve with the x-axis, we're talking about this region in here. So we can say that the average value of g is equal to 1 over b minus a on the closed interval of a to b of the function 1 plus the square root of 1 minus x squared. Do you see kind of why I wrote it as x to the 1/2 though? But instead of as a square root. But here's the next question I have for you. Do we know how to take a square root integral yet?
No.
So if you ran into some example like this, you would have to go back to the methods that we do know, which is to use your what? Okay, but you still don't know how to take the half of a function. This is a chain rule in derivative terms. So we don't have a chain rule yet. So what I'm saying is, okay, sure, great, we can write this. So here, this simplifies to what? In order to find this average value, you have to go back to what we talked about the other day, which is geometric shapes and their area. So what's the area of the shape of the rectangle? You have a base of, a height of, so 2 times 1 gives you. So the base area is 2. The top is a semicircle, so the area of a half circle. What's our radius? So the area of the top of the circle is 1/2 pi. So the total area of this whole region is 2 plus 1/2 pi. So you have half, then 2 plus half of pi. So half of 2 gives you 1. Half times a half gives you a 4. Or you could write it as or 1. You're fine. So then the next question becomes, so we're going to get there. I don't have a rule for it yet. The next question is, when does g of x take on this average value? What's nice about this? What's nice? Your ones cancel, right?
Wow.
What do you know about a circle of radius 1, regardless of the fact that it was shifted up 1 unit? Circle of radius 1 is our unit circle. Circle of radius 1 is our unit circle. So, when on the unit circle am I going to get to my pi fourths? Okay, square root of 2 over 2. If it's a trig function, you take sine pi 4 square root 2 over 2. So think about the fact that we now have 1 minus x squared to the 1/2 power. So this right here represents a circle. If you square rooted both sides, or I mean, if you squared both sides, get rid of your square root. Subtract away your 1. You have a negative x squared, get rid of your negative. Square root that. You reduce it, you will get root 2 over 2. You'd have to common denominator, and then you'd have to make a substitution in for each pi, but that's fine. Sorry. That's the most gruesome of them.
Is it not plus or minus?
So if you did the plus or minus, the negative one's excluded again. which is around the root positive. Like it's outside your interval. Okay. It's not. Yeah, the negative one. So how can we relate that to MVT? Well, MVT itself is kind of like saying an average in a way. It's saying, okay, the slope of the secants equal the slope of the tangents, and when do the slope of the secants equal the slope of the tangents? So the mean value theorem for integrals basically says that if you're finding an area under a curve between A and B, then there is some number C between A and B whose function value you can use to form a rectangle that has an area equal to the area under the curve. What is an expression that could be used to determine the area under the curve from A to B? So what expression do we use to find the area under the curve? What expression do we use to find the area under the curve? We use the integral from A to B of f of x dx. What would the area of this rectangle be? The width is what's that? Okay, and what's its height? So they went into the midpoint and they said that C exists here, and we're saying f of C is the height of the rectangle. So the base or the width is b minus a, and the height is f of C as depicted over here. This value of f of C is what we would consider to be the average value of f on the interval of a to b. So what we are saying is that f of C times the quantity b minus a is equivalent to saying f of C equals, because we just said it, this f of C represents the average value of f. So it's 1 over b minus a times the integral of a to b. So mean value theorem says that there exists some point C on the closed interval a to b such that the average value of the area under the curve equals the average value area. So the formal definition for MVT is that f is continuous. That sounds familiar. F had to be continuous on the mean value theorem for derivatives. That f is continuous on the closed interval a to b, then at some point C in a to b, we have that f of C will equal 1 over b minus a of a to b of f of x dx. where again, that integral with this b minus a represents the average. So in summary, the mean value theorem simply states that for integrals, that at some point within the interval, the function must equal its average value. The theorem does not actually find the value for c. It simply proves that c exists. So let's use our calculators to find an MVT of a complicated value once again. So we have x minus 1 squared. Now we could do this one the long way. How could we do this one the long way? Okay, even easier than graphing it, we could calculate this integral by hand by doing what to the function? By FOIL. It would stay x minus 1 now. So again, we could FOIL this and say x minus 1 and get x squared minus 2x plus 1. And then I could use my power rule for this. So I could actually find 1 over 3 minus 0 of 0 to 3 of x squared minus 2x plus 1 dx. I can also compare it to what I find on the graphing calculator. So for practice, this becomes 1/3. What's the antiderivative of x squared? What's the antiderivative of negative 2x? Yeah, remember the 2 stays on top with the x squared. So actually what happens here is those 2's end up canceling. And then a single constant gets in x. The 1/3 remains outside. You wonder why they have the lines in them. Okay, 3 cubed becomes 27 over 3, which becomes 9. 3 squared is 9, so you end up with 9 minus 9 plus 3 minus 0 cubed, which is 0, 0 squared, which is 0, plus 0. So again, 9 minus 9 is 0, 0 plus 3 is 3, so you get 3 times 1/3. So what this says then is, and let's go back and use NINT. So let's confirm that my 1 is correct. So take out your calculators, hit math, hit 9. Type in x minus 1 squared, put a dx, and make sure you put your bounds as 0 to 3. What do you get? That's what you should get, is 3. Because if you put 3 in 1, it should be 0 to 3. It's second under instead of bracket 3. So now my question is, okay, why did he get 3, but I said the answer is 1? I know why you got 3, and I know I got 1. Compare what you did to what we did on the board. Yeah, we didn't use the 1/3 on the calculators. So what you found was the area under the curve, not the average area. So what I had, and I had you do it on purpose. I didn't tell you to put a 1/3 out in front of that. I wanted you to see, okay, why he get 3 or why did I get 1? So what you found was this. You used the calculator and you found this, which is 3. So the area under the curve from 0 to 3 is 3, but the average value of that area then becomes 1 because we're looking at it from 3 to 0. So this again right here is the average value.
I think that's what I was trying to do.
Gotcha. So how could I use my graphing calculators to help me find the value with which the average value will occur? So the question is, this says, okay, by the mean value theorem, f of c must equal 1 on the closed interval 0 to 3 for f of x equals x minus 1 squared. It says at what point in the interval does the function assume its average value? So to find that point, we would say that, okay, f of c has to equal 1, therefore x minus 1 squared has to equal 1. So what x value is going to make that true? So you would square root this, so you'd get x minus 1 equals the square root of 1. But this is the case where you would want to put both the plus and the minus on your square root. So then you'd get x equals plus or minus root 1 plus 1. So the positive 1, so square root of 1 is 1, right? So this is really like plus or minus 1 plus 1. So 1 plus 1 would give you 2. 1 minus 1 would give you 0. So we're not 0 and 2 both in there. So what that means is by the mean value theorem, f of c would equal 1 on that closed interval, and the value c equal 2 and c equals 0 will be the points at which the average value of f equals f of c. Let's do 6, and then we'll be done, and we'll make all the conjectures tomorrow as a good summary, because that's what they are. So find the average value of the function on the interval without integrating. So again, if we do it without integrating, we're appealing to the geometry of the region. So we have one, oh wait, we did this one. You're good. Yep, you're good. I forgot I moved my example up earlier in the lesson.